Good morning, everyone. Welcome to lecture 8 on the course Data Structure and Algorithm. Uh, so today we shall discuss on binary search algorithm. Okay. So in the previous class we talked about linear searching algorithm. We demonstrated the algorithm, formulated the algorithm, and also we have seen the demonstration of the program implementation. Okay, so and we have seen that the complexity of linear search algorithm is in the order of small n. That means it's a linear time complexity function. Okay, the growth of the time complexity function of linear searching algorithm is linear. That's straight. Okay, but today we shall actually discuss about binary searching algorithm, where we will see that this binary searching algorithm is faster compared to linear searching in in uh, in in some specific cases. Okay, so also we will see that the time complexity function of binary searching algorithm is not linear, rather uh, mm, rather it's a or big O notation of log n base 2, and log n base 2, uh, the graph of log n base 2 always lie below the straight line, I mean order of n. Okay, the polynomial linear polynomial n. Okay, thereby we can conclude that binary searching is in most of the cases is faster than linear searching. Obviously we will have some assumption uh, to make binary searching algorithm faster compared to linear searching. Okay, so So I have shared my screen. Hope you can see my screen.
Yeah, we can.
So let's take a similar problem which we have used in the last class. So an array of 10 elements size we are considering, and let assign the values like 1, 2, 3, 9, 11. Next 17. Okay. So we considered an array of 10 elements, but the elements in this case, as you can see, are sorted in ascending order. 1, 2, 3, 9, 11, 13, 17, 25, 57, and 19. So this is our assumption. The array elements are in ascending order. Okay, sorted in ascending order. So this is our assumption to apply binary search algorithm, which is not like in case of linear searching. They may be in any order. Okay. Now let's take two pointers or two trackers or normal two variables, for example. One is this one, let's say we call as min index. Another here is max index. It's pointing towards 90. Okay. So we must use these two trackers or pointers of normal variables, which are pointing towards something leftmost element and the rightmost element of the current data structure. In this case, it is an array. So we know that array index starts with, from programmer's perspective, it is starting with 0. Okay, so as we have to develop the algorithm, let's start the index with 1, and if there are n number of elements in the array, so index of the last element is n. Okay, fine. So basically this variable, this will be equal to 1 and this will be equal to n. Okay, now what I am doing, I want to take a number from the user. Let's say I want to search a value which is, let's say, 40. I want to search a value, an element of which value is 40. So what shall we do? We will go to the middle of the array. Okay, the middle position of the array can be calculated by this formula. Let's say another variable, mid index, is equal to mean index plus max index by 2. Okay, that is the. So this is our formula. So using this, let's try to, in this case, our n equal to 10. For example, in our case, n is equal to 10 for this example. So then according to this formula, it will be 1 plus 10 by 2, that is 11 by 2, that is 5.5. So what we shall apply more specifically, so let it be first bracket, this first bracket, yes. Sorry. And then floor function. Okay, so what we are doing, we are applying a floor function on this overall value. For example, in our case, mean index equal to 1, max index equal to 10. So 1 plus 10 equal to 11 by 2, that is comes to 5.5. So floor of, in this case, our floor of, it will be in a floor of 5.5, which is nothing but the greatest integer function. This is your 5. Okay.
Yes.
So 2, 3, 4, 5. So it will come to the position 5. Or you may apply also ceiling function. That's not a problem. Okay. 6, 7, 8, 9, 10. So we are here. So this max index currently is heading towards this element. Okay, and this is 5. So now at this situation, we want to compare whether this element of searching, that is 40 is greater than at that.
Sir,
Yes.
sir, it should have been mid index, no? You wrote max index there.
Yes, sorry.
Mid index in the point 11, fifth element.
Oh, okay. I'm telling mid index, but writing next. So yes, the mid index. So at this position, we want to compare whether 40 is greater than the element at mid index. In this case, it is 11. So is 40 greater than 11? Yes, true. So what is the conclusion? If 40 is greater than 11, so 40 may be equal to that element if equality holds, or if it is strictly greater than 11, then 40 will not be present the left part of this 11.
Mid index minus
40
1.
must be lying to the right part of the array with respect to 11. Am I correct?
Yes, sir.
Because according to the assumption, the array elements are sorted in ascending order. It's not possible that 40 will be lying to the left. It is only possible that 40 may be lying to the right. Okay, so what we do, this is our condition checking. So 40 greater than 11. So then we will now try to search the element 40 in this part of the array. Okay, so next we are extracting the sub array from the original array. Okay, what we are doing for the next iteration, that is 5 elements of contradiction. Exactly. And then it is here as for 40 is strictly greater than 11, so it may be lying in this sub array 25, 57, 90. Okay, so now what you are doing, here in the sub array you are trying to search the element 40. So automatically the size of the sub array on which you have to perform the searching operation is getting reduced. Earlier you are attempting to search 40 in a data structure with size 10, but now you are applying searching of 40 in a data structure in this array of which size is equal to 5. Okay, so as this element was used earlier for comparison purpose, so that was used, but these 4 elements were not further are not be used in further searching processes, right? So that is the saving of time. Time is invested whenever you are doing some operation like comparison. Okay, in this case we have done a comparison operation 40 greater than 11, so some time will be invested in that operation, but there is no time at all will be invested, okay, using these 4 elements, so that is saving some time. Okay, so again this will be your new mean index. This will be your new mean index. Okay, and this will be your new max index. Okay, in this sub array, and again you will find out, calculate the mid index, and that mid index will now be equal to sorry, index equal to floor of, what is this mean index value? 13 corresponds to 6. So mean index is now 6, max index is still 10. So 6 plus 10, that is 16, divided by 2, that is 8. And floor of 8 is 8 itself. So you got the value of mid index equal to 8. That means it is now referring towards, it is now referring towards 6, 7, 8, 25. Okay. So now when you are comparing whether 40 is greater than 25 or not. So if it is greater than 25, yes, it is true in this case. So it will not be lying to the left of 25. It may lie to the right part of the array. Okay, with respect to 25. So again, what you are doing, you are extracting or dividing the array into two parts, or extracting the sub part from this array. That array is something like this. This is sorry, not 25. This is 57, and this is 90. Okay. So now your revised mean index will be this one. Revised max index will be. This index is not changing; it's still same. So it is your 57 corresponds to 9. So new mean index value is 9, but max index is still 10. So what will be your mid index? Your mid index will be equal to 19 by 2. 9 plus 10, 19 by 2, that is 9.5. Floor of that is actually 9.
9.
Okay, so that is actually referring towards 57. So at this situation, what you are doing, you are checking whether 40 is greater than 57 or not. Is it true? No. What is true? That 40 is less than 57. So this is true. So this is true. For the first time, less than comparison is being satisfied. So true. So 40 less than 57. If this is true, what you have to do? Okay, so in this figure, I can't show you that thing, that phenomena. Okay, so but I'm literally saying that what will be done, that your mean index, this is your mid index. Your revised mean index will be the same as before. Okay, that means in our case it is 9. Mean index is 9, max index is 10. So mean index in this case will not be changed. You have observed in this pattern that whenever greater than sign is satisfied, mean index is changing, max index is not changing. Okay, but whenever less than sign will be satisfied, mean index will be same, max index will be modified. And what will be the max index? I can't show you here in this case. Just literally saying that max index will be in this case the existing mid index minus 1. So in our case, what is the existing mid index? 9. So 9 minus 1, that is equal to 8. So max index will try to come here before 57. And okay, but what will happen after that? If mean index is 9 and max index is 8, that means what is happening? What is happening here? Let me use some red color. Here, mean index becomes greater than max index. Right? Mean index becomes greater than max index, 9 greater than 8. That is the my ultimate situation we are having. So once this is achieved, mean index greater than max index, immediately you have to understand that crossover phenomena, this is called crossover phenomena, occurs. Okay, this is the stopping criteria. That means you have to stop here. You can't proceed further because throughout the program, throughout the algorithm, this condition should be always true, that mean index should be always less than or equal to max index. Okay, it can't be greater than max index. If it is greater than max index, you have to stop there because crossover has occurred. So this should be the execution criteria of the iterations. Okay, I hope you have understood a little bit. Okay, now this is our scenario. This is the logical part we have understood so far. And whenever you are stopping, you are just checking whether the element 40 is equal to the element represented by mid index. So is 40 equal to 57? No. And then crossover occurs. Okay. So here crossover occurs plus the element 40 is not at all equal to the element represented by mid index. Then you have to understand that 40 element is not at all present in the array data structure. Okay, so you assume that number 40 is which you were searching. It is not 40. Let's say you were searching 57. So if it is 57, this greater than sign will not be true, less than sign will not be true. Okay, but crossover occurs. That means you are stopping there, but you are checking whether the element 57 you are going to search is equal to the element pointed by mid index or not. Yes, it is equal to the mid index value 57. Then you are understanding, okay, 57 is present in the array at the position given by mid index. Okay, so I think we should go for the algorithm. I think it will be more clear. So first you have to read in X, the element you want to search, and like the previous linear searching algorithm, you read okay, you read all the elements into the 1D array. You may do that. That is optional. So for I equal to 1 to n, where n is the array size of array capital A. Okay, and read ai. I is in suffix. Capital A equal to set of the vector of ai, okay, where I is equal to 1, 2, dot dot n. Okay, you can put there any belongs to R or integer values, no problem. So now this is your reading data reading part, read X. Then okay, then you are calling a function that binary search, okay, and you may pass that information in the array, let's say capital A, binary search. So, and okay, now let's develop the function. binary search function. Binary search. So here you have to initialize three trackers: mid index, mean index, and max index. So mean index equal to 1, max index equal to n. So you require the information of the element size, that is n. Okay. Then mid index, it is not required to initialize. That's all. Max index equal to n. Next, max index equal to index plus max index a by 2, and floor of this I am writing. You will actually, I can't draw here, so you will write that thing, floor of this overall function, overall expression. Okay.
So that will be mid index.
Symbolically, you will draw here the floor symbol. Okay. So max index is this one. So this should be written inside a block of a loop. You see,
So that
we
will
are
be mid index.
have to use a loop. Yes.
So that will be mid
So that will
index.
be mid index. Yes, sir. Mid index होगा
Mid index the
Fine,
floor
fine,
will
fine.
not have the rest.
Oh, fine. So see, we did a loop. We are doing the same thing. Initially, we are given an array based on the min index value. Comparison with the value in the mid index, we are breaking the array into two parts: left part, sub part. Either part we are considering for the next iteration based on condition checking. Right. Next, we are rejecting one sub part, accepting the other sub part in the next iteration, and again doing the same comparison of the element of searching and the element at mid index. Based on the comparison output, we are again dividing the current array into two subparts: left part, right part, accepting any one, rejecting the other. So we are requiring a loop. Okay. Right. So we require a loop. So some condition should be there. So this loop should continue till we face a crossover. And what is the crossover phenomena? How can it be modeled? What is the stopping? That is the stopping criteria, and that mathematically it can be modeled as this condition checking: mean index
greater than max index.
max index. So if that condition becomes true, we have to understand crossover occurs, and that there you have to stop. So the condition for the loop execution should be the opposite: mean index less than or equal to max index. So for the time being, let's strictly impose this condition: mean index less than max index. Okay, so under this loop we are doing this. So while this okay, we are doing now comparison. First, see, mean index is the leftmost point, max index is the rightmost point, and in some middle position is the mid index. Now we are comparing the user given value x with the value at mid index. So if x is equal to a, in bracket I'm writing, so this is not the algorithm we are supposed to write, but a in suffix it should be mid index in subscript. So I'm unable to write here because it's a simple text. So you understand a bracket mid index means in a suffix you have to write mid index. Okay, so I'm writing only mid index. So if x is equal to a index, if equal to is there, that means already something is found, something is successful. So you display that x found at mid index. So x found at mid index. Okay, and then you stop there. And before stopping, you have to raise a flag. Okay, searching has been found successfully. So let's say we are using a flag variable. This is a normal variable. We call it as a flag to raise at any intermediate situation whether found searching is successfully done or not. Once searching is successful, we want to modify this value of variable found as equal to, let's say, 1. And to if and initially we must do this, that is globally found equal to 0. So this found will be equal to 0, will remain equal to 0 till the searching of x is found is done successfully. Okay, so found equal to 1 and then stop. And if now what if x is not equal to a of mid index? So else if x is greater than a of mid index, so it will be lying in the right half part. So for right half part, what you are supposed to do, if it is greater than a of mid index, so mean index should be revised, max index will be same. So mean index is showing you all these cases are based on true, and whenever these cases are done, whenever the greater than sign was true, and every such cases you have seen mean index is being modified, but max index is always stay. Okay, so if this condition is satisfied, you have to revert the mean index, not the max index. So how can anyone tell me? Try to understand. For the first case, mean index equal to 1, max index equal to 10. Now based on the condition checking, 14 greater than 11, 40 is greater than value at mid index, that is 11. So the 40 may be lying in the right half part. So you are revising the mean index with 13, the index of value 13. What is the index? 6. Why 6?
So mid index plus 1.
Yes.
Mid index plus 1.
So mid index is 5. Just plus 1 is actually the 13 value. So that means you have to add plus 1 with the mid index to get the revised value of mean index. I hope all of you are agree with us.
Yes.
All are getting understood, right? Okay.
Yes, sir.
So okay. So next, mean index equal to mid index. That's all. Else part, that means x is less than a of mid index. Then what you are doing, that max index, any other person please try to answer the question. What can be the max index, revised max index? For example, we are not searching, let's say 40, let's say we are searching, let's say 03. Okay, so is it true, greater than sign true? No, it is less than 11. So if
The
it is
mean
less-
index minus 1.
what? Please repeat again.
The mean index value minus 1.
Please louder.
The new max index will be mid index minus 1.
Mid index minus 1. So that means that 03 number may be lying in this part. So your mean index should be this, max index with this. So to get this index, it is nothing but 1 less than the mid index. Okay. Okay. So okay. So once we are done, the while part is done. So here we are ending the end while. Okay. And after the end while loop, if we see that the flag value has never achieved 1, that means in this while iteration, while loop, the found value was never modified. What does that mean? That element x is not at all present in the array. That's for sure. So x is not found in A. Okay. And if okay. I hope this is clear. Is it clear?
Yes, sir. Yes.
Yes, sir.
Yes, sir.
Okay. So it's already 11:20. So I wanted to show you the program implementation. It's already there. So it's a very simple code. So I'm just telling you the code. It would be better that, okay, let me do a copy of this program. Okay, that same thing I have implemented over here. Okay, whatever algorithm we have seen, side by side we can implement the code. So initially, yes, some array we have initialized with elements 15. So now is like your x. So min index equal to first index, max index equal to last index, mid index just declared, and some found equal to 0. So whatever we have done in the algorithm, same thing we have done in the code. Enter the number you want to search, scan a percentile day x. Then what is there? Okay, so should I call a function? Okay, let's call a function. I search. Paste and just for your simplicity, just to make the code align the same identical with the algorithm, I'm just doing this, though it is not required. Okay, so list and end. See, so by mean index, okay, we can also do this. to 1, max index equal to n, mean index, index, and found equal to 0. I may not require this line. Okay. Yes. Now, after C, this line, while mean index less than max index. Okay. So yes, I didn't explain this case equality. There may be equality. I mean, mean index greater than index is the stopping criteria. So the opposite is less than or equal to. So that's to be used. Okay. So I thought that equality condition. I will okay, in some other class, someday I will show, in the next class I will show you one case where equality holds. This equality will be utilized. So mean index is then equal to max index. Mid index equal to this C. Mid index equal to this by 2. As mid index equal is an integer variable, even this becomes a float. So by implicit type conversion, it will be converted into an integral value, and that integral value is nothing but the float of that value. Okay, so you don't have to apply explicitly a float function. So mid index equal to min plus max index by 2. So if num is equivalent to C, if num is your x, okay, that information have to be passed. List in x. Just wrapping up. So okay, x int x. Then this is your x less than equal to list or a index. Then yes, it is found at the number found at mid index plus 1 found equal to 0. Oh, okay. So then it should be 0. From programmer perspective, this is index starts with 0. Am I correct? So this is the slight adjustment between the algorithm and the code. So found equal to 1, break. If num, or you can provide here return 0. So if num greater than list, this is a, mid index equal to mid index plus 1, else max index equal to mid index minus 1. Similar what we have done, just copying the algorithm in the code. Okay. In the list. Right. So I hope it is fine to all of you. First index equal to 0, last index equal to 14. This is required. Okay. Let us compile the program. Okay, so enter the number you want to search. Okay, for your understanding, for your reference, what are the elements are there? 14, 16, 20, 21. Okay, these are the elements. So let's say we want to search, let's say 21. Some middle value, probably 45 or 47, it will be the middle value. So then we can, yes, we can, okay, let's search 20. And also we'll try to search 89. So 20, 89, and some value, let's say 30. 30 is not there. So 20, 89, and 30. Yes, you want to search. Let's say first 20. So 20 is found at position 3. Is it position 3? Yes. Okay. Next, let's iterate again. So 89 is found at position number 14. So there are few elements. So this is the 14th position with respect to the lemma. So that is also fine. See, the code has been implemented immediately after the algorithm. Once you have done the algorithm in a good manner, Coding implementation is not a very big deal. You just have to do some little adjustment in soft programming. So now let's say 30 we want to search. 16 is not found. Okay, what happened? 16 is not found in the list. Okay, some problem is there. Oh, X. Yes, 30 is not found in the list. I hope this is okay to all of you. I will share the code. If any question, you can ask me right now. If any question, you can ask me right now. So no question as of now, so we can close our class today. Thank you for the listening the lecture.